Hello, this is my submission for the 3B1B competition, the Summer of Maths Exposition 1. Good morning, everyone, and welcome back to my channel. If you're new here, my name's Agni Sen, and I'm 15 years old. Today, we're going to be talking about the Fibonacci sequence and the golden ratio. Let's start with the question. Have you ever counted the number of seeds on an intact sunflower? Or have you ever counted the number of fronds on a pine cone? If you have, the number you got is probably a Fibonacci number. But what is a Fibonacci number? Simply explained, a Fibonacci number is a number that occurs in the Fibonacci sequence. The Fibonacci sequence is a series of numbers that was discovered by Leonardo of Pisa, an Italian mathematician about 800 years ago. The Fibonacci sequence occurs when a given number is the result of the sum of the two numbers that precede it. We know that the sequence starts with 0 and 1. By doing this, we can deduce the next terms in the sequence. 0 plus 1 equals to 1. So the third term is also 1. 1 plus 1 is 2. 2 plus 1 is 3. 3 plus 2 is 5. 3 plus 5 is 8. 8 plus 5 is 13. 13 plus 8, 21. Next is 34. The next number is 55, 89, and so on. The numbers in this Fibonacci sequence will keep getting bigger as the sequence moves on till infinity. So we're going to stop at 89 for now. Like any mathematical sequence, the Fibonacci sequence can also be represented with a formula. The formula that mathematically represents the Fibonacci sequence goes as follows. F of n, which is any term in the Fibonacci sequence, will equal to n minus 2, which is the term 2 terms before n, plus n minus 1. This is the term that directly precedes n. So, Fn equals to n minus 2 plus n minus 1, provided that n is greater than or equal to 2. It is important to remember that the numbering of the terms in the Fibonacci sequence starts from 0. So, f of 0 will equal to 0. But this is actually the first term. F of 1 will equal to 1. But this is actually the second term. And f of 5 will equal to 5. But this is actually the sixth term. Now that we have that clear, let's look at an example of this formula. F of 6. Let's take f of 6. We know f of 6 will equal to f of n minus 2, where we know 6 is equal to n, so that will be f of 4, plus f of n minus 1, which is 6 minus 1, so 5, plus f of 5. Okay? So, f of 6 equals to f4, which is the fifth term, so 3, plus f5, which is the sixth term, so 5. So f6 equals to 8. And we know that's true because we know f6 will be the seventh term. So there's 0, 1, 2, 3, 4, 5, and 8. So we know f of 6 equals to 8. And we can say this formula is true. Okay, now let's talk about the golden ratio and what it really means. According to the great Greek philosopher Pythagoras, the most beautiful and pleasing proportion is created when a line is divided into two parts such that the ratio between the smaller part and the larger part is the same as the ratio between the larger part and that of the whole line. This ratio is called the golden ratio or the golden mean, and it is represented by the Greek letter phi. The ratio has an approximate value of 1.618 is to 1. Before we start, we can establish that the golden ratio is represented by the Greek letter phi, which is spelled as PHI. This has an approximate value of 1.618 1.618. This is the establishing information about the golden ratio, but we still don't know what it really means. So let's dive deeper into this. Let's start by finding the quotient of dividing consecutive terms in the Fibonacci sequence. Okay, so let's start by 1 divided by 0, which we know is undefined. Let's skip a few terms and go on to 3 divided by 2, which we know is 1.5. Let's go to 5 divided by 3, which we know is the same as 10 divided by 6. So that's 1.667. Let's move on to 13 divided by 8, which we know is 1.625. If we go further and go on to 34 divided by 21, we get the answer as, let's just put this into the calculator, 1.619. And if we go one step further of going 89 divided by 55, we get our answer as 1.618 recurring. Okay, now as this is happening, we begin to see an interesting trend down the Fibonacci sequence. We begin to see that the ratios between consecutive terms of the Fibonacci sequence gets closer and closer to the golden ratio as the terms get bigger and bigger. So what we can say in not so many words as an easier explanation would be, so what we can say is that the golden ratio is the limit of ratios of successive terms in the Fibonacci sequence as n tends towards infinity. Mathematically, this can be represented by the following equation. So we will say the limit of f upon n, or f of n upon f of n minus 1 equals to phi as n tends towards infinity. This limit equation explains the golden ratio. Another thing that is very interesting is the fact that as the Fibonacci sequence grows bigger and bigger, it slowly converts to a geometric sequence with a common ratio as phi, the golden ratio. So if we write down the Fibonacci sequence from 0 till 233, we can see that as the numbers grow bigger and bigger, the ratio between them becomes the golden ratio. So an interesting way to prove that would be f of n equals to f n minus 1 into phi. And this doesn't work in every scenario, because if you look at 0 and 1, 0 times phi will not give you 1. So let's just say for a marker, this only works provided that n is greater than or equal to 8. Okay, so let's take an example. 144. Let's take 144, which is the 13th term. So it's f12 equals to f11 into 5. So that's 144 equals to f11, which is 89, into 5, 1.618. So let's see, 144 will give you, if you do 89 into 1.618, that gives us 144.002. So as we can see, the number is very, very close, but because 89 is not a very big number in the Fibonacci sequence, it will not give it completely exact, but it's still quite close. Rounded off to the nearest whole number, the answer is the same. Okay, let's talk about another thing that I find quite interesting. We already know that phi equals to 1.618. This is given as in decimal form. Now, it is possible to convert this to fractional form. And if we do that, the answer we get is root 5 plus 1 upon 2. You guys can put this in your calculator to check if you want. Now, this answer is the fractional form of phi. Now, we can also plug this into an equation to get a better understanding of finding bigger numbers in the Fibonacci sequence. To do that, we say f of n equals to f of n minus k multiplied by root 5 plus 1 over 2 raised to k. Okay, in this case, k is some constant, which is the difference between f of n and a small number in the Fibonacci sequence whose value we already know. Let me give you an example. Okay, so f of 12 will be equal to f of 12 minus k into root 5 plus 1 upon 2 whole raised to k. Okay, so f12 equals to f of 12 minus, in this scenario, we have to assume a value of k. What we should do is take a small value of k so that we can get our answer to the most accurate degree. So in this scenario, let's take 4 as our example. So f of 12 minus 4 into root 5 plus 1 upon 2 whole raised to k, which is 4. Now, f12, we already know is the 13th term of the Fibonacci sequence because it starts from 0. And therefore, we know that the 13th term in our long series over here will be 144. Okay, this is our 13th term. So we already know the value of f of 12. We're just doing this example to cross-check our formula. So 144 equals to f of 12 minus 4, which is f of 8, which we know is the 9th term in the sequence. So f of 8 equals to 21 into root 5 plus 1 upon 2 raised to 4. And if we put that into the calculator, the answer we get is 6.85. Okay, so when we multiply these numbers, we get 144 equals to 21 into 6.85, which when you put in a calculator is 143.936. Okay, as you can see, these numbers are very, very similar. The accuracy is very, very close. In this scenario, it's not exactly accurate, but if we were to round up to the nearest whole number, the answers would be the same. And that's how we know that this method also works. So, to recap, the Fibonacci sequence is a series of numbers where any given number is the result of the sum of the two numbers that precede it. The golden ratio, also known as phi, which has the value of 1.618, is the limit of ratios of successive terms in the Fibonacci sequence as n tends towards infinity. Okay, now this all may seem a little confusing and theoretical. An interesting way to visualize this is by drawing squares. Let's go to that next. To start the sequence, we draw a 1 by 1 square. Then we draw another identical square adjacent to it. Then we draw a 2 by 2 square and a 3 by 3 square. So on, the pattern continues for a 5 by 5 and an 8 by 8 square. This pattern goes on until infinity. As we draw arcs in each square of this figure, the shape that forms turns out to be a spiral. In geometry, when the golden ratio is applied as a growth factor, you get a special kind of logarithmic spiral known as a golden spiral. From its natural manifestation in hurricanes, seashells, and flowers, to its explicit use in architecture and art like the pyramids and the Mona Lisa, the golden ratio is everywhere around us. Thank you for watching, everybody. Whoever's reached till here, I really appreciate it. If you did enjoy this video, please consider subscribing and liking the video. It really helps me, grow on YouTube. So, thank you. That's all. Mr. Sanderson, if you're watching, thank you so much for making this platform so we can share our maths explainers with the world. I've always wanted to make maths explainers and I've never known how to do it or never had the motivation to do it, but you gave me the inspiration to go forward with it. Thank you so much.